welcome back to second lecture of MathCamp. In this lecture we are going to cover basic topics of the set theory. As well, we will formally and informally describe the meaning of the function and we will solve a couple of examples. Let's start by introducing the idea of the set theory. We are going to develop a working knowledge of the methods and ideas of set theory through an informal discussion. Generally in mathematics, the meaning of the word set is used to represent a collection of objects which are viewed as a single entity. For example, very basic things like the crowd, team, or even all Agicon PhD students can be viewed as sets, and each individual, for example in case of team player, seen as an element or member of the set. So usually we denote sets by capital letters and the individual members by lowercase letters. And when element belongs to some set, let's say set X belongs to set S, then we say that X is in S. So for example, if S is a set which has numbers 2, 4, 6, then 2 is in set S. Let's do one more example. Suppose we want to know members of set X. But suppose we define A as a set which includes all x's such that x satisfy following expression. So x squared minus 1 equals 0. To find what are the members of A, we will need to solve this. X squared is 1, so x is plus minus 1. A minus 1, 1 is our set. We say that a set A is a subset of a set B if every element of A also belongs to B. Or in other way, we write that A is a subset of B if and only if for all elements that belongs to A, then A is in B. In other words, if we find some element that belongs to A but does not belong to B, then in that case A is not a subset of a set B. The other thing you can note that when we say A is a subset of B, we does not rule out possibility that we may have that B is a subset of A. If both these two happens, then we say that A equal B. In other ways, A equal B if and only if A is a subset of B and B is a subset of A. For example, suppose we have two sets, set A which has following elements, and set B with following elements, then it is easy to show that A is equal B, since whatever elements we take from A it belongs to B, and all elements in B belongs to A. So we have equality here. If we have situation when A is a subset of B, but A is not equal B, then we say that A is a proper subset of B. And we write this following way. Let's do one more example. Suppose A has these two elements and B, C are following sets. So we want to prove that A is a proper subset of B. To show this, we need to first show that A is a subset of B, then show that A is not equal B. So for the first one, you can see that it's actually easy to show, since 2 is in B and 3 is in B. Here, from definition of the subset, we have that A is a subset of B. Now, if you remember the definition of equality, we have that set A is equal set B if and only if A is a subset of B and B is a subset of A. So if one of these expressions are not satisfied, then we don't have equality. So we prove that A is a subset of B. Now, if we find any element that belongs to B but does not belong to A, then we don't have that B is a subset of A. And it's easy to show, since 6 does not belong to A. So from here, B is not a subset of A. And from here we can conclude that A does not equal to B. The same way can show that B is not a proper subset of C. Even it's not a subset of C, since B has the element 6, which is not in C. Let's introduce one more notation which is very useful in proving things. When we say all x's such that x is in S and x satisfies some property P. So in this case, we want the set of all elements that x is in S and x satisfies property P. For example, if S is a set with the following elements, then if we want all elements that belongs to S and all positive, then we will denote this as following. And definitely these elements are these 4. The same way you can choose some element that satisfies the property that you want to impose on set. Now let's talk about some algebraic properties of sets. Particularly, we will talk about the union, intersection, and complement of the set. So from the two sets A and B, we can form a new set which called the union of A and B, and we denote this as A union B. To understand this, suppose we have some set A and B. So union is when we select all elements. So in other words, this is the set of all elements which belong to at least one of the sets A, B. So intersection. So in this case we select elements that belong to both sets. So for example, if this is our set A and this is our set B, then we select the elements that belong to both A and both B. When the sets are disjoint, so the sets are disjoint if they don't share any element. So you see that intersection is empty set. So in other words, two sets are disjoint if A intersection B is empty set. Difference or complement of the set. So the complement of B relative to A of two sets is all elements of X such that X is in A and X does not belong to B. In this case, we are looking on elements that are in A but does not belong to B. If the sets are disjoint, then they don't share any element, so the complement of A relative to B is A itself. Let's do a couple of proofs related to set relations. So the first thing we are going to prove is commutative law. So we want to prove that I intersecting to B is equal B intersection to A. A intersection to B is all x's such that X is in A and X is in B. And B intersection to A is again all y's such that y is in B and y is in A. So from these two we can see that equality follows, since remember the equality means that we need to show that A intersection to B is a subset of B intersection to A and B intersection to A is a subset of A intersection to B. So from the following definition it can be seen whatever element we take that belongs to A intersection to B, this element should be in B intersection to A and vice versa. Let's do second example. So we want to show if A is a proper subset of C and B is a proper subset of C, then A union of B should be proper subset of C. We have that since A is a subset of C, then for all x in A, so this means x should be in C. The same way, if B is a subset of C, then for all y in B, y should be in C. Now, if you remember the definition of the union, these are all Z such that Z is in A and Z or Z is in B. Here, if we take any Z, take randomly Z that belong to A union on B, then from here we can say that Z is either on E or Z is in B. But we know that A is a subset of C and B is a subset of C. So from here Z should be in C. Since the element we take was randomly, from here we can conclude that A union of B is a proper subset of C. Note that we can't say that it's a subset of C, since to prove that C is a subset of A union B, we don't have much information. We also can have a sequence of sets A1, A2, AN, and etc. And we denote the union of the sequence of sets as all x's such that x is in AI for some I. So if at least for one I x is in AI, then we have the union. For the intersection of the sequence of sets, we need all x's such that x is in AI for each I. So another way to say this is that for intersection we require that element be in all sequences. So now let's define what we mean by power set. So if let A be a set, the power set of A is the set of subsets of A. So this set is all B's such that B is a subset of A. Let's do example, very simple one. We want to find the power set of the C which has element 2, 4, 6. So the power set is all set of subsets of A. Set of subsets of C are empty set, each element individually, and all possible pairs of the elements. But the thing that you may already noticed is that previously our sets were not ordered. That is, for us there were no difference where the specific elements of the sets were. If we have pair of objects x and y, if we want to distinguish one of the objects, say x, as the first member and y as the second member, we enclose objects in parentheses. And we refer this as a ordered pair. The set of ordered pairs with the first component in A and the second component in B are denoted as following. So for example, if A is a 4, 6 and B is a set of elements 4, 5, 6, then 6, 4 and 6, 5 are ordered pairs in Cartesian product of A, B. So the other thing you may note that 6, 4 is also in Cartesian product of A, B. But those are the different elements. 6, 4 and 4, 6 are different elements. Now let's define what we mean by Cartesian product. So Cartesian product is the set of all elements such that and A is in A, B is in B. Now we are going to talk about one of the important topics in mathematics, about functions. In our everyday life, we always deal with relationships that exist between one collection of objects and another. Graphs, charts, and curves are devices for describing spatial relations in a quantitative fashion. Mathematicians refer to certain types of these relations as functions. For example, the area of square is a function of its edge length. If edge length is x, then the area is x squared. First, let's give the informal definition of function as following. Given two sets A and B, we informally define a function as a correspondence which associates with each element of A one and only one element of B. The set A is called domain and B is range. So if we try to visualize it, so if this is our set A and this is our set B, then function takes elements from X and gives us element in B. The simplest example is an identity function. fx is equal x. So it takes x and gives us the same element. The other simplest function is the absolute value of x. If we try to graph it, then it looks like something like this. So now let's define function formally. A function f is a set of ordered pairs x and y, no two of which have the same first member. Another way to say it, a function f from x to y is a subset of Cartesian product of x, y, such that for each x in x there exists a unique y in y. Let's give definition of two more types of functions. So the first is a one-to-one or injective function, and the second is surjective or onto functions. Let f be a function from x to y, and we say f is one-to-one if and only if for all x1, x2 is in X, such that fx1 is equal fx2, then x1 is equal x2. Or in other way, we can say that if x1 is not equal x2, then fx1 does not equal to fx2. The second type is onto or surjective functions. So function f is onto if and only if for each y in y there exists x in X such that y is equal fx. If a function is one-to-one and onto, then it's called bijective. Now let's do a couple of examples to understand what is the meaning of one-to-one functions. So consider a function fx is equal x squared. The question is it one-to-one? When it goes from 0 to infinity to 0 to infinity. So in this case, our domain is 0 to infinity and the range is also from 0 to infinity. If we try to visualize it, so x squared is a parabola, our function looks like something like this. Now we want to prove that it's one-to-one. So let arbitrarily take 2 points x1 and x2 that belongs to 0 and to plus infinity, and fx1 is equal fx2. It means x1 square is equal x2 square. So now what we want to show that x1 is equal x2. So the thing you need to note that since range is a positive and the domain is also positive, then x1 square is equal x2 square implies that x1 is equal x2, and we prove that the function is one-to-one. If f is one-to-one and onto, then we say f as an inverse, and we denote it as following. Basically, f is a function which brings us back to whatever we are. So if we try to visualize it, if it's x and this is y, if it's if function f is one-to-one and onto, then f takes us to the y, and then inverse brings us to the same point. But we have not defined yet what we mean by composite function. So since this can be written as fgy, so we haven't defined what is the meaning of this. So given function f from x to y and function g from y to z, composite function is defined as a function from x, z. So intuition is following. Suppose those are following sets x, y, and z. Then the function f takes us to y and the function g takes us to z. Then the composite function takes us from x to z. Now we want to prove that function fx, which is defined as, we want to find the inverse of this function. Let's write y is equal following. Then if we multiply this equation by exponential of x, then we will get minus 1, and from here so what you can note that this equation is a quadratic. So if it's quadratic, we can use quadratic formula to find ex. But since exponential of x is always positive, then we can discard the minus sign. So from here we have that exponential x is equal y plus over 2. If we take logarithm of both sides of this equation, then we will have that x is equal log y plus minus logarithm 2. So therefore f inverse is, let's do a couple of more examples about the one-to-one functions and about the inverses. First example, suppose we have two functions f and g. So we want to show that if f and g are both one-to-one, so is the composite function. So now let's prove this. We do a direct proof, so let fg are both one-to-one. And what we want to show is that the composite function is one-to-one. Let's take xy that belongs to A. What we will show that the composite function g of x is equal composite function g of y. Then this implies that x is equal y. Now let's assume that the equality of composite functions holds. Therefore, g of x is equal g of y. Since g is one-to-one, from here fx is equal fy. But f is also one-to-one. Then we have that x is equal y. Let's do one more example. In this example, we suppose that we have two non-empty sets and f is a function from A to B. We want to prove that f has a right inverse if and only if f is onto or surjective. Since we have if and only if, we need to do it in a two direction. Suppose f has a right inverse function g. Note if you don't know what means right inverse, it means composite function of fg is identity function. It means fg b is equal b. Now let's do our proof. Let b is in b. What we need to do, we need find element a in A such that fi is equal b. So let I is equal gb. Then the composite function of fg, so is equal the identity from the definition, and this is equal b, and the one direction is done. Now let's do the other direction. So what we assume that f is surjective, and we want to show that f has a right inverse. This right inverse maps, let's say some function which is function h, from b to a such that fh is one identity. So now let's define h as follows. For each P in B, we know by surjectivity there exists at least one A in A such that FA is equal B for some choice of A. So now from definition it is true that HB is equal B for all B in B. From here is identity.